All right, so I'm going to go ahead and get started. My name is Stephanie Weiss. I am a second-year medical toxicology fellow at UT Southwestern and Parkland Memorial Hospital in the North Texas Poison Center. And before I went to medical school, I was an organic chemist, which is what my PhD is in. And I put together this talk to help other toxicology fellows and faculty too, just so that people are hopefully going to have to do a little bit less memorizing and be able to recognize some common groups of structures. Okay, so I'm going to start by talking about some of the history of organic chemistry and why do we have all these crazy naming systems that we have anyway, and just so people have some kind of perspective about the organic chemistry nomenclature systems, because there's actually two parallel systems that you're probably familiar with. And the first thing that you should know is that organic chemistry is a fairly old science compared to a lot of the other medical types of sciences that we think about. And because of that, a lot of times the compounds that we're talking about, people were able to synthesize them and work with them before they were able to really figure out what the structures of them were. So before we had modern instrumentation where we were able to figure out what the 3D structures were, even sometimes what the molecular formulas were, we were already able to go in the lab and synthesize things. And so because of that, then there grew up two separate naming systems for organic compounds. And the one that you learn when you take an organic chemistry class as an undergrad is called IUPAC. I'm going to talk more about that in just a second. But that's a fairly recent thing compared to the original system, which was called the common nomenclature. And so there's quite a lot of names that are still used from before IUPAC came about. And these are the ones that people sometimes go, where did that name come from? So I mentioned IUPAC, and as I said, that is the systematic nomenclature that people learn in their undergrad organic coursework, and that is the International Union of Pure and Applied Chemistry. So this is an organization that comes up with standard naming procedures for organic compounds. And the big issue with IUPAC names is that they tend to be pretty cumbersome and long in many cases. And so, as I mentioned, there's a lot of compounds that we still use that have IUPAC names as well, but nobody ever uses those IUPAC names. And so you need to just learn the common names. The common names, there is some system to them as well, but it's separate from the IUPAC system, and it's not quite as nice and systematic in comparison to the IUPAC system. So before we go through some examples of individual compounds, I wanted to just review some of the common organic groups for people. So just so everybody remembers, these are the hydrocarbons here. You see on the top left an alkane, which is all sp3 hybridized carbons, so no double or triple bonds. And then if they do have double bonds, then they're called alkenes, or a triple bond, which we don't see very often in nature, is an alkyne. And then at the bottom there you see a benzene ring, or if it's a substituent, it's called a phenyl. And then at the bottom right you see an X is there to stand for a halogen atom, so you can have an alkyl halide, where the X can be any one of the halogens. Just to remind everyone also about the counting system in organic chemistry. So for a 1, we use the prefix methyl. For 2, we use ethyl. 3 is propyl. 4 and 5 are in the middle there, butyl and pentyl. At the bottom, you see the 6-carbon chain, which is hexyl. And then I skipped 7. We don't see as many with 7. And then you see an 8-carbon chain, which is octyl. Some of the branch chains have special names as well, special common names as well. And again, people often use those instead of the IUPAC names. So that one at the top left is one that you will see fairly often, which is isopropyl. And that is like the propyl group, but instead of being attached to the N carbon, it's attached to the middle one. The analogous 4-carbon chain to that is the one next to it, which is isobutyl. And then you can call the 5-carbon analogous chain isopentyl, but in fact it has a common name as well, which is amyl. So people generally don't use isopentyl, they'll use amyl instead, but amyl means isopentyl. So it's a common name of a common name there. At the bottom, I've just shown some of the other common structures of the other butyl substituents. So N-butyl, N stands for normal, and what that means is the 4-carbon chain with the group being attached to the final carbon on the chain. If you attach it to a straight chain to the second carbon, one of the two middle ones, that's called secondary or S-butyl, or sometimes sec-butyl, people will call it. And then if you have, for the isobutyl, instead of attaching it to the end, if you attach it to the middle carbon, you're going to end up with a tertiary butyl group, or T-butyl. We don't see a ton of those, but there are a few drugs that have T-butyl groups on them. All right, so now what I'm going to do is go through some examples just to help people keep in mind how you actually name these. And the first one here is, you can see it has an isopropyl group. I haven't talked about any of the heteroatoms yet, but this is an alcohol, and it's isopropyl attached to an alcohol, and therefore then it is isopropyl alcohol. And this, of course, is one that we're interested in quite a bit in toxicology because this is a secondary alcohol. We're going to talk more about what that means in a little bit when we talk about primary, secondary, tertiary. But basically, this one gets oxidized up into a ketone instead of to an aldehyde and an acid. And so, unlike most of the toxic alcohols, isopropyl alcohol does not cause an anion gap acidosis. Here's another example, and I mentioned to you before, this is an isopenyl group, but we don't call it that. We call it amyl. So it's an amyl group, and then that other heteroatom group that's attached to it is a nitrite group. And so put those together and you get amyl nitrite. And amyl nitrite is also of interest to us in toxicology. This is a potent vasodilator that can release nitric oxide, and that is able to relax involuntary muscles and blood vessels and can cause hypotension and can also serve as an oxidizing agent and cause methemoglobinemia. So these drugs and other similar ones like them were used quite a bit. It was a popular 1980s club drug for gay men that sometimes you still see around. They're called poppers. So I mentioned before about alkenes, which are hydrocarbons with double bonds, and these have special names as well. So the IUPAC names are the ones that are in parentheses, and you see at the top there the 2-carbon alkene, which is the simplest, is called ethene under IUPAC nomenclature, but the common name for that is ethylene. So nobody really uses ethene. Below that, you see the 3-carbon analog of that would be called propylene, would be the common name. The 4-carbon one below that, which is branched, would be called isobutylene, and that's the same thing as 2-methylpropene. And then at the bottom there, you see one that is called isoprene, and we're not going to talk about that today, but I'm going to be doing a talk in the future about natural products chemistry. And so isoprene is a building block for terpenoids, which are seen in a lot of natural products, and so that's definitely a structure that you'll see over and over again in nature. When you use alkenes as substituents to things, again, they have special names. So the very simplest one is a simple double bond to CH2, which is you see at the top left there, and that's called methylene. The one next to it, which normally would have been ethylene, it's not ever called that, it's called vinyl. Okay, so again, this is just a common name you need to learn, is vinyl. The one next to that is not called propylene, it's called allyl. So you won't see as many allyl structures, but vinyl shows up quite a bit in several compounds of toxicologic interest, and I'm going to show you some examples of that. Here's one that is an interesting compound. This is an example of a methylene compound, and so you can see there on the far left, this compound is hypoglycin A that comes from unripe ackee fruit and some other similar ones like lychees. And the thing of interest to this is that it gets metabolized into something called MCPA, which is the structure you see on the right. And what is MCPA? Well, the M stands for methylene. And you see there's the methylene group that's been circled in red. And the C is for the cyclopropyl group, which is that 3-membered ring. And then the acetic acid is a common name for the structure on the far right there. So this is methylene cyclopropyl acetic acid, or MCPA. And this is the agent or the metabolite of hypoglycin A that is going to inhibit carnotylacyl-CoA transferase, which leads to decreased gluconeogenesis and decreased beta oxidation. And that's what causes the severe hypoglycemia in patients that eat these unripe fruit. It actually also affects a second enzyme called glutamate decarboxylase, and that enzyme is involved with synthesizing GABA from glutamate, and so therefore people can get seizures with this as well. So they can get a bunch of other not so good symptoms like acidosis and coma, but the things of interest for this Jamaican vomiting sickness that people can get are that they get the hypoglycemia and also the seizures, and those are the mechanisms by which that happens. So that name of that compound is hopefully going to be a little easier to remember. If you remember, methylene is that double bond CH2 substituent coming off of that cyclopropyl group. So we've already talked about vinyl and allyl. If you look up at the top there, you see the vinyl again and the allyl again. And analogous to those, when we're talking about aromatic rings, an aromatic ring substituent is called phenyl, as I've mentioned, and that's the analog to the vinyl group. And then the analog to the aromatic analog to an allyl group is called benzyl. Okay, so the difference between them, in the same way that allyl has that extra CH2 compared to vinyl, benzyl has that extra CH2 compared to phenyl. All right, so now we're going to do a little bit of practice, and here you see you've got a chloride on this group. It's a C double bond CH2, and I've already told you we don't really call that the ethylene, or we would call it ethylene, or you could call it ethene if you followed IUPAC. But remember, when you're using the alkene as a substituent, the common name for it is actually vinyl. So because you have a vinyl group and a chloride group, when you put these together, you end up with vinyl chloride as the common name of this, with chloroethylene being another potential common name if you named it by the ethylene with the chloride as a substituent. And this is definitely one that's of interest to toxicologists. It is an IARC1 agent, which means it's a known carcinogen, and specifically it leads to hepatic angiosarcoma. And another thing that's good to know for this one is that it can cause acroasteolysis and Raynaud's syndrome of the digits. So these are definitely things that are common for tox boards and in-service exams. Here's another example to look at, and I've circled the part of interest that I want you to focus on, and what you see there is, again, a methylene group. And this structure might be a little bit hard for people to name otherwise, but the fact that there's a methylene may give you a little bit of a clue. This is actually methylene blue. And so if you ever thought about, well, why is it called methylene blue? Well, it does have a methylene in it. It has that CH, actually there's no H, there's a C double bond in there. And in this case, it's double bonded to a nitrogen. So methylene blue, of course, is of interest to us because we can use it to treat hemoglobinemia, but it also is of interest because it can actually cause hemolysis in people who have G6PD deficiency. And it's also potentially serotonergic. It has some MAOI activity as well. All right, so of course, nothing can ever be totally easy in organic chemistry, just like everything else. And so here's some exceptions to these rules that I've been showing you so far. If you look at this structure on the left here, you see that you have 2 chlorines and 2 hydrogens on a single carbon, which would be dichloromethane, and that's correct. That would be the IUPAC name for this, but it also has a common name, and the common name that it has is methylene chloride. So there is, even though there's no double bond in this molecule, there can't be, right, because there's only 1 carbon, but even so, it still has that same nomenclature. So unfortunately, this is just an exception that you have to learn, that this is still called methylene, even though there's no double bond. And dichloromethane is also a compound of toxicologic interest for several reasons. Like any hydrocarbon, it can certainly cause CNS effects, and it can cause defatting dermatitis. But the thing that's of interest for this is if people ingest it, it is a liquid at standard temperature and pressure, and if you ingest it, it can actually cause delayed carbon monoxide poisoning. Here's another one that's an exception to the rules we've talked about. So the IUPAC name of this is oxirane, and it's a 3-membered ring here. It doesn't have any double bonds in it, but the common name of it does have an ethylene in it. It's called ethylene oxide. And I'm going to show you where the genesis of that name came from, because it's actually not as kind of crazy as it seems once you understand how this compound is synthesized. Ethylene oxide is also an important one to be aware of. That's another IARC1 known carcinogen in humans, been associated with cancer of the breast and the bones, and it can also be a sensitizer as well. Okay, so as I said, why do we even call this ethylene oxide when there's no double bond in it, and you guys have probably heard of ethylene glycol, which also doesn't have a double bond in it, so why do we call it ethylene glycol? And this has to do, again, with historical reasons and having to do with these synthetic pathways for these compounds, and the fact that before we were able to really figure out the structures of compounds, we were able to figure out things like how many units of unsaturation are there, but remember, a unit of unsaturation can either be a double bond or a ring, and initially people weren't always able to tell the difference. Is it because of a ring or because of a double bond? And so if you start with ethylene, which does have a double bond, and you go ahead and you oxidize that then you get ethylene oxide. So you use a catalyst and some oxygen, and you end up with this structure here that we've already seen. And so you can see that now the double bond is gone, and you have this ring instead. So the reason why ethylene oxide has ethylene in it is because it comes from ethylene. Analogously then, if you keep reacting this and you basically react it with some acidic water or some basic water, now you're going to end up with ethylene glycol, which is the structure there at the bottom right. So ethylene glycol is definitely something that shows up quite a bit in toxicology. We know that it can cause acidosis, which is primarily thought to be due to the glycolic acid metabolite, and it can also cause renal damage, which is thought to be primarily due to the oxalic acid. But now, if you've ever wondered where did that name come from, just keep in mind that these are all synthesized from ethylene, and so because the ethylene has that common name, then the others do that come from it as well. Okay, we talk a lot about epoxides and how reactive they are. And so maybe if you've wondered why are they so reactive, this has less to do with the chemistry of them and more to do with the fact that there's a lot of ring strain in these. So what I'm showing you here on the left is a methane molecule, and you see that the angle there, it's a tetrahedral shape, and the angle of that is 109.5 degrees. And in contrast, I've actually drawn cyclopropane and not oxirane, but it's the same idea. What you see here is that the angle is much smaller, it's only 60 degrees. And so because it wants to be at 109 point, and I use that wants loosely, but it would prefer to be at a 109.5 degree angle, and it's stuck instead at 60 degrees, then you have quite a lot of strain. And so it relieves that strain. Basically, when you pop one of these three-membered rings open and the angle changes from 60 degrees to 109.5, it reduces the strain from that ring quite a bit. And so it's a much more favorable configuration for the molecule. Okay, so now I'm going to talk about, we've mentioned ethylene glycol, and I've talked about the ethylene part, but I have not talked about the glycol part. And so here what I'm showing you are two structures that have identical groups, either on the same atom or on adjoining atoms. So if you look on the far left, you see what's called a vicinal diol, and vicinal means that they're neighbors, they're vecinos, they're right next to each other, one on one carbon, one on the carbon next to it. As opposed to geminal, think like Gemini, like twins. They're on the same carbon. So if you have them on adjoining carbons, it's called a vicinal relationship, as opposed to if they're on the same carbon, it's called a geminal. All right, so now specifically, again, everything has to be a little more complicated than you thought possible. Here, if you take something that is a ketone or an aldehyde and you make a gem diol out of it by adding either acidic or basic water, then you get the gem diol like we just saw on the prior slide, but that has a special name, which is a hydrate. We do see a few of these. They're not especially stable, so there aren't tons of them around, but we do see a few of them in toxicology. And so I'm going to show you a common example of this, which this is actually the parent compound here, which is an aldehyde. And so this is called trichloroacetaldehyde. And so basically when you form the hydrate of this, here's what you get. And so you see here that you have, again, the trichloro, and now instead of having the acetaldehyde, you have the hydrate. And so this is actually called chloral hydrate. So this is, again, one that's commonly comes up in toxicologic discussions. And it ends up getting metabolized further to trichloroethanol, which is an agonist of the GABA A receptors and can cause a lot of the same kind of sedative hypnotic symptoms that you'd expect from something that would bind to GABA A, including coma and respiratory depression. And then of historical interest, if you mix this with with alcohol. So you have a solution of chloral hydrate and alcohol. That's called a Mickey fin, which is kind of an interesting historical background. All right, and I've already mentioned about glycols. So we talked about ethylene glycol in particular. So here you see, again, the same that I showed you before, where you start with ethylene oxide and you open it up using acidic water to get the ethylene glycol. And you can actually keep going on and on with this. So say we add a second ethylene oxide and we form the structure shown at the bottom there. That is diethylene glycol, which is also a toxic alcohol. So if you look at that, we haven't talked about ethers yet. We're going to in a minute. But you see it also still has the two primary alcohols on it, just like the ethylene glycol does. And just like ethylene glycol, therefore, it does cause acidosis, and it does cause renal damage, although it's not by the same mechanism as ethylene glycol, because this structure does not form oxalic acid. And you can, again, keep going if you like. Here you have 3 of them attached together, which is named triethylene glycol. And you can keep going and going and going, many repeats of this, then you will get polyethylene glycol, which is what you see at the bottom right here. And this compound is relatively non-toxic because it's not very well absorbed, and that's why we can use it as a laxative and for bowel prep. All right, so I've been mentioning some of these structures already, but just to remind everybody about these functional groups, on the far left there you see an amine, where you have an organic nitrogenous compound. Next to that is an alcohol, which we've talked about quite a bit. The sulfur analog of an alcohol is called a thiol. So anytime you see thi, that's coming from sulfur. Next to that is an ether, which we've mentioned already, like how the diethylene glycol had an ether bond in it. And then the sulfur analog of that is a thioether. All right, and I've already been kind of alluding to this primary and secondary nomenclature talking about alcohols, but I want to make explicit for you that when we talk about alcohols being primary versus secondary versus tertiary, it's not the same thing as when we talk about amines. So if you look at the alcohols on the top row there, you see that we're talking actually about the carbon that is next to the oxygen. So the primary alcohol is a CH2 with one R group and then OH attached to it. The secondary alcohol has 2 R groups on there plus an OH, so similar to how when we talked about isopropyl alcohol. And then you can also have a tertiary alcohol where there's 3 R groups attached to that carbon. You cannot have a quaternary alcohol ever, though, because you cannot have a carbon with 5 bonds to it. So tertiary is as far as you can go with alcohols. And that's a little bit different than with amines, because when we're talking about primary, secondary, tertiary, and quaternary amines, we're actually talking about the substituents that are attached directly to the nitrogen itself. So not to the carbon next to the nitrogen, but to the nitrogen itself. So you can actually have, if you look on the far left, a primary amine that has 1 R group to it. The secondary then would have 2 R groups on it, and a tertiary amine would have 3. And then if you go ahead and add a 4th one, then the quaternary amine, which is positively charged, you see on the bottom right there. So I just wanted to, like I said, make that explicit because I don't think people always realize that this nomenclature is a little bit different for amines than it is for alcohols. One other group that you don't probably see a ton of in an undergrad organic class, but that's actually of some significance for toxicology, are hydrazines. And hydrazines have an NN bond to them. You see a structure of a generic one there. And here's an example of one. This is a drug, isoniazid. And isoniazid is actually a prodrug. It has to be activated by a mycobacterial enzyme called CatG, and it forms an acyl radical then that can bind to another enzyme called INHA. And what that enzyme does is the mycobacteria uses it to synthesize its cell walls. So it forms a compound called mycolic acid. And so what this does then is block that synthesis. So this is showing one of the metabolic pathways for this. And what you see is that it gets acetylated. And we haven't talked about the carbonyl compounds yet and the carbonyl groups yet, but we're going to be doing that pretty soon too. But you see the second compound at the top there is the acetylated compound, and then that can be broken up, and you end up with one product is the isonicotinic acid, which is not toxic, and then that one at the bottom right there can also be potentially problematic. That's acetylhydrazine, and we're going to talk about acetyl groups in just a minute. So isoniazid, as I mentioned, is important to know because it has many bad side effects. The neurological ones, things like peripheral neuropathy and seizures, can be treated with pyridoxine. whereas the GI things, so things like hepatitis, really cannot be. And then there's some hematologic and immune effects from it as well. And then that acetylhydrazine at the bottom can also be a bad actor that can actually cause an idiosyncratic hepatic necrosis. So not only can the isoniazid itself be the acyl radical can be a problem. Radicals are always reactive too, but some of the metabolites are also problematic. Okay, so I've already mentioned some of these carbonyl compounds, and what I've shown you here is from left to right, you're seeing them in increasing reactivity. So if you look at the bottom, you see the ketone and the aldehyde in the middle. They're kind of medium reactivity, with amides and esters being less reactive, and acid anhydrides and acyl chlorides being more reactive. And you really won't see acid anhydrides or chlorides too much in toxicology. Those are the kind of things that we use in a chemistry lab to do synthesis. But you will definitely see many amides and esters and carboxylic acids, which is at the very far left. And I put it there because under physiological conditions, the carboxylic acid would be deprotonated and be a negative anion. So it's not very reactive. This is just another structure here, a cartoon to show you how these carbonyl compounds that I was just showing you are combinations of other functional groups that you already know. So basically, if you mix together an amine and a carboxylic acid like you see on the left, then you end up with an amide. And if you put together a carboxylic acid with an alcohol, then you end up with an ester. And then on the far right, if you put together an alcohol with something called an isocyanate, which we're going to be talking about a little bit more, you can get something called a carbamate. And carbamates are of interest too. They're present in some pesticides, which have cholinergic properties. All right, so talking some more about diisocyanates, here's an example of a molecule that shows up quite a bit for toxicological interest. This is more of a occupational exposure. And so if you look at this, this is another one that, again, has a common name that isn't necessarily what you would expect. So if you look at what the structure of this is, you see you have that methyl group in the very center, and it's attached to two phenyl groups, and then those each have the isocyanate on them. And so when you name this thing, what you're going to call it is methylene for that methyl in the middle, diphenyl for the two benzene rings, and then diisocyanate for the two isocyanate groups. And this compound is of interest because it's an allergen and a sensitizer, although it's not quite as bad as the other famous diisocyanate, which is this one. All of these exist in mixtures of different forms, and I'm going to show you a little bit more about that, but the methylene diphenyl diisocyanate pretty much is always, as I've shown you at the top, it's pretty much all in where the substituents are in the 1 and 4, kind of on opposite sides of the ring compared to each other. The second one here, and we haven't talked about common names yet for substituted benzene rings, but the common name for a methyl benzene ring, nobody ever calls it methylbenzene, is toluene. So here you see two different toluene diisocyanates. You see a 2,4 and you see a 2,6. So the 2,4 is the one on the left. And that one's present in about 80% versus the 2,6, which is more hindered, is present about 20%. And this is another one that's big for occupational asthma, and it's called bathtub refinisher's lung. So that's toluene diisocyanate. All right, so these prefixes for carbonyls also have special names. Here's one that's just the carbonyl itself with a hydrogen attached to it, so it's an aldehyde, and that is a formal group. The next analog out would be acetyl, and then you'd go on to propional. Butyryl would be the next one, and 5 is not pentyl, unfortunately. It is valer or valeryl. So again, that has a common name that you just have to learn. I don't know why 5 carbons are always special and have, the 5 carbon, instead of being isopentyl, it's called amyl, and why the 5 carbon here is called valeryl, but 5 carbons somehow always have their own names. I want to show you one other naming convention that's based on numbering the carbon chain away from the carbonyl group. So if you think of the carbonyl carbon as the number 1 carbon, the one next to it is alpha, the one next to it is beta, then gamma, then delta, then epsilon, and so forth. So you can use Greek letters to number the carbon chain away from that carbonyl. So you don't count the carbonyl carbon, you start with the carbon that's adjacent to it, and that is the alpha carbon. So here's some examples of naming these. This is one that I think everybody will recognize. This is methanol. And methanol, as we know, can be oxidized up in the body by alcohol dehydrogenase to formaldehyde. And then formaldehyde can be oxidized up by aldehyde dehydrogenase to formic acid, which you see here on the far right. So in all three cases, you have that form prefix in front of them. So nobody calls it methaldehyde or methoic acid. It's going to be formaldehyde and formic acid. And this, of course, is of interest because it does cause an anion gap metabolic acidosis, as well as can potentially cause optic nerve damage and blindness. Here's another good example that's common for toxicology. And here we're going to practice doing the Greek letter naming system. So if we look at this, there's a 4-carbon chain, and on the 4th carbon, which would be alpha, beta, gamma, right, because we don't count the carbonyl carbon, then that has a gamma hydroxy. And since it's a 4-carbon chain, it is a butyrate. So I've lettered these for you, alpha, beta, gamma. And when you put that all together, you end up with gamma hydroxybutyrate. And GHB is a GABA B receptor agonist, which is also a naturally occurring neurotransmitter in the body, and it's a drug of abuse as well, often by bodybuilders. It causes release of growth hormone. Okay, this is actually an inorganic naming convention, but I'm going to show it to you because it can be kind of used for naming some organic compounds as well. So what I'm showing you here, if you look down to the 3rd row where it says reference, so this is looking at the amount of oxidation of acids. And so what you see is the reference one, then you have this is the us and ix system. So in the same way like how iron can be iron 2+ versus iron 3+, and then you call it ferrous or ferric, and it has to do with how oxidized it is, you can do this with these oxyacids as well. So if you have one less oxygen attached to it, then it would be us acid, or if you have one more, it would be per whatever it is, ic acid. And then if you have 2 less oxygens attached, it would be hypo in front of that as a prefix. And I'm going to show you an example so this is clearer. So if you look at this structure at the far left, this would be hypochlorous acid, okay, because this is the one that's got 2 less oxygens than the reference. Compare that then to this structure, which is chlorous acid. And then if we add one more oxygen, that makes chloric acid. And then finally, if we add 4 oxygens, you end up with perchloric acid. Okay, so again, the reference one is the one that is ic, in the same way that we have for iron, ferrous, and ferric, and with the one being more oxidized being ic and the one being less oxidized being us. You don't always have all 4 of these types of structures. So for iron, there's only 2. For this example that I've shown you with the chlorates, there's 4. So to name the ones on the far ends, you would use the hypo and the per. And why am I showing you this in an organic talk? Well, basically because we can still use this same system of nomenclature even for organic compounds. So here's an example of how this can be extended. So this compound that you're seeing here, this is an ethylene. It has 3 chlorides attached to it, and therefore it is trichloroethylene, or TCE. And TCE is of interest also. That's another IARC1 compound, which is a known carcinogen. It can cause kidney cancer and non-Hodgkin's lymphoma. Also has the same kind of CNS depression activity that you would expect, and it has some hepatotoxicity. And here is the compound that would be analogous to it with 4 chlorides attached to it. So we don't call this tetrachloroethylene, even though we could, but we don't. Instead of calling it tetrachloroethylene, using that naming convention I just showed you with the chlorous and chloric acids, we actually call it perchloroethylene. So remember, per means you have one more bond to the oxidizing atom, or one less electron in the case of a metal. So this tetrachloroethene, or tetrachloroethylene, again, we never use that name. We call it per instead, and this is a common name, and that naming convention is similar to what I just showed you for the inorganic acids. Okay. Couple other of naming conventions I just want you to be familiar with. This one is nor-des. Nor and des mean the same thing. They both mean one less carbon. And the opposite of nor and des is homo. Homo means one more carbon. So those are opposites to one another. Nor and des mean the same thing. Homo, and they both mean one less. Homo means one more. So here's an example. This is the amino acid cysteine. And so you may have heard of this compound, which is similar to cysteine, except for there's one more CH2 here compared to cysteine, and this is therefore called homocysteine. And homocysteine is known, if you have elevated levels of this, that's associated with cardiovascular disease and coronary artery disease. Here's some more nor and des examples. You may recognize this particular catecholamine. This is epinephrine. And so if you've ever thought of, well, what's the difference between epinephrine and norepinephrine? Well, the difference between the two is that norepinephrine is missing one carbon compared to epinephrine. So epinephrine, you can see, has a methyl group attached to that amine, and norepinephrine does not. Otherwise, the structures are exactly the same. Here's another example that's a common drug that we see as an antidepressant, which is, this is venlafaxine right here. And you may be aware that there is a similar drug called desvenlafaxine. So you're wondering, well, what's the difference between venlafaxine and desvenlafaxine? So they're not enantiomers. Sometimes people think that. It's not like citalopram and escitalopram. The difference between them is this. Desvenlafaxine is missing this methyl group right here that I've circled. And so the difference between, they're otherwise exactly the same, except for venlafaxine has an extra O methyl compared to desvenlafaxine, which is a metabolite of venlafaxine. Here's one more example that is kind of quasi-obsolete, and I'm putting this here just because not only does this provide a good example of a common name, but it also emphasizes the fact that sometimes this common nomenclature can really be tricky. So I already told you before when we were talking about the different types of butyl substituents and groups that nor can also be short for normal. And that's the case here. So what you're seeing on the far left is the amino acid leucine, which is one of the 20 common amino acids. And so this is a common name for, so leucine, if you look at it, it has an isobutyl group as its side chain. And so norleucine is the N-butyl group, or norbutyl, and so that is called norleucine. And again, in this case, nor is normal. It does not mean one less carbon. If you count, they both have 4 carbons in their side chain there. I haven't talked about this functional group yet. We don't see a ton of this in toxicology. This is an interesting kind of compound called an alene, and it has, that middle carbon is actually sp hybridized. Those 2 double bonds are not, they're actually perpendicular to one another. So there's no resonance between them. So it's almost like a triple bond, and it's a very rigid structure, and it's called an alene. So you won't see a ton of them, but here's an example of one that is of importance for toxicology. So if you look at this structure and compare it to the norleucine above, because that's what it's named after, and you see you've got the leucine part of it, you've got the amino acid part of it, and then the side chain there has 4 carbons in a straight chain, similar to norleucine, only instead of all those sp3 hybridized carbons, you have an alene in there. And so when you name this, then it's alenic norleucine. So this is one that, like I said, uses multiple naming conventions. The alenic part comes from the alene, and the nor part comes from the fact that this is norleucine, which is the parent name of this compound. And alenic norleucine is interesting. It comes from the mushroom Amanita smithiana, which is from the Pacific Northwest. And most of the time when you hear about mushroom toxins that cause short-term GI symptoms, nausea, vomiting, diarrhea, abdominal pain, they tend not to have long-term effects. But in this case, actually, this compound does. It causes short-term GI effects within a few hours of ingestion, and then a few days later it can also cause renal failure. So not something that we see a whole lot, but definitely something that's important to know about. All right, we've already talked about some of the different substituted benzene rings. Unfortunately, again, aromatic chemistry is old chemistry, and so most of these have common names that, again, just have to be learned. So you've already seen benzene at the far left, and we have not mentioned this before, but it's important to know. Benzene is an IARC1 agent as well, so known carcinogen. It causes a lot of leukemias as well as aplastic anemia. The one next to it there is toluene, and toluene is important because that's a compound that gets deliberately abused sometimes. It can get a psychoorganic syndrome. I'll talk more about it in just a minute. And then some of the others here that are important to know, phenol on the far right at the top would be important to know. On the bottom you can see benzaldehyde, second from the left, and then benzoic acid. And then the amine form that's analogous to phenol is called aniline. And so you see some anilines as well. Those are used often as dyes. So getting back to toluene, as I mentioned, this does get deliberately abused. People huff this sometimes. It can cause dementia and polyneuropathy and also cerebellar symptoms and tremors. So the metabolic pathway of this is of some interest, and it's good for practicing for naming things too. So here's toluene itself. And so the way that it gets metabolized is by oxidation. So the first thing it gets oxidized up to is this compound, which we've already mentioned, and this is called benzyl alcohol. Benzyl alcohol is of interest because it gets used as a preservative. It's bacteriostatic, and it's been used in IV fluids before. So there was actually a case, some cases in the 1980s of something called neonatal gasping syndrome in premature infants, and there was a metabolic acidosis that was occurring because the infants weren't able to complete this metabolic pathway that we're currently going through all the way to the end. So besides the acidosis, they ended up getting hypotensive and having cardiovascular collapse. So the next thing that happens to the benzyl alcohol is that it gets oxidized up to the aldehyde, and so benzyl alcohol then would be benzaldehyde. That then would get oxidized up to the acid here, which is benzoic acid. And so this, up to this point, this pathway is very similar to what we see for other toxic alcohols. There's one more thing that tends to happen, and this is why the small babies got the neonatal gasping syndrome, is because they weren't able to do this last step, which is a conjugation step that occurs when you add glycine to benzoic acid, and you form a product called hippuric acid, which is what you see on the far right there at the bottom. So hippuric acid is the primary urinary metabolite for toluene, and that's actually something we can measure, and it will indicate that somebody's been exposed to toluene. I've already kind of alluded to the positions on the ring. So if you have a substituted benzene ring and you're talking about how the substituents are related to one another, the position next to where the substituent is called ortho. That's the 2 and 6 position. The one that is 2 positions away is called meta, which is 3 and 5 position. And then the opposite position is called para. And so I have included, sometimes you can get reactions that substitute on the original carbon, and that position has a name too. It's called ipso, but you're unlikely to see very much of that one. So the di-substituted aromatic rings, many of them have special names as well, and they're named both with the special name, the special common name, as well as with the substituent pattern. So here you see you have a benzene with 2 methyl groups that are attached in an ortho configuration, and these are not called dimethylbenzene, not that easy. This has a common name called xylene, and because they are ortho to one another, it is the O-xylene. And so if you have an O-xylene, then you got to have one that is meta, and that's the M-xylene. And if you have an O and an M, then you're going to have one that's para, and that is the P-xylene. And xylene is another common hydrocarbon. Here you see a similar one that's like a benzene with a hydroxy group and a methyl on it, and again, not called methylphenol, not called hydroxytoluene. It has a special name as well, which is cresol. So here you see the orthocresol, which is O-cresol, and this is the meta version, or M-cresol. And here you see the para version, which is P-cresol. So this is actually a compound of interest for toxicologists as well, and some historical interests. Here you see you've got 3 cresols here, and they are all orthocresols. And in the middle there you have a phosphate, and so this is actually a compound that's tri-orthocresol, because there's 3 of them, and then phosphate. So TOCP, or triorthocresyl phosphate. And this is a compound that's it's an inhibitor of acetylcholinesterase and butyrylcholinesterase, and historically it was of interest during Prohibition in the 1930s. It was added to an alcohol product called Jamaica ginger, and it caused what's called the ginger Jake shakes. So it causes some polyneuropathy, and some people even got paralyzed because the alcohol product was deliberately adulterated with TOCP. This is just to show you some of the common names of heterocycles that contain, some of them are aromatic, some are not. So they're rings that contain other atoms besides just carbon. Some of the important ones to note, you have imidazole, which is third from the left, that's present in histidine and histamine, which comes from histidine. On the bottom there you see you have pyridine and pyrimidine, which are some of your nitrogenous bases, so those get used for things like making DNA. Here's an example of a common polyaromatic hydrocarbon, poly meaning multiple, aromatic being aromatic ring, so it's more than one aromatic ring. This one has a common name of naphthalene, not called dibenzene. And naphthalene is of interest because it can cause methemoglobinemia and hemolytic anemia, especially in people that have G6PD deficiency. And you still find it around a little bit in mothballs, although a lot of mothballs don't have naphthalene in them anymore. Here's the similar analogous compound structure that has 3 rings to it. That's phenanthrene. Here's one with 4, and that's called pyrene. And this one is of interest because it's a polyaromatic hydrocarbon that we see quite a bit in terms of, it was of historical interest, and also that we see as a known carcinogen, which is benzo-A-pyrene. So where does that name benzo-A-pyrene come from? Well, if you look at the structure of pyrene at the top, you see that you have 4 rings, and the A ring is the one at the bottom left, and that the difference between them is that the benzo-A-pyrene has an additional benzene ring attached to the pyrene, and so it's benzo-A-pyrene. You can have other pyrenes too, they don't all have to be A. A couple more examples. Here's some polyaromatics that have substituents on them. So this one here is a naphthylamine. This is the 1-naphthylamine. You can have a 2-naphthylamine as well. So these compounds are also known carcinogens. They cause bladder cancer. They're IARC1 as well. Here's some other examples. This is an alcohol analog. This one is called 2-naphthol. And here's another one that is a metabolite of pyrene. And this 1-hydroxypyrene. These compounds are of interest just because they're urinary markers for polyaromatic hydrocarbon exposure. Another one that you may run into, this is an indole, and indoles are fairly ubiquitous in compounds that contain serotonin or are otherwise affected by serotonin. So serotonin itself contains an indole. This is serotonin right here, as well as the amino acid tryptophan, which I don't have the structure of drawn here. But this is serotonin itself, and serotonin has another name. Serotonin is the common name. It's also called 5-hydroxytryptamine, with the trypt coming from tryptophan. So what happens to this when it gets metabolized? Well, the first thing that happens is it gets metabolized up to an aldehyde and decarboxylated, deaminated. So this structure is a 5-hydroxyindole acetaldehyde. So you can see that the indole part is the part on the left, and then you have the 2-carbon carbonyl group on the right, which is the acetaldehyde, and it's an aldehyde which continues to get oxidized up to the acid. And the name of this then is 5-hydroxyindole acetate, or acetic acid, the way I've drawn it with the proton on there. A couple more structures to recognize. These are quinones, and you can have a quinoline, which has the nitrogen there next to where the 2 rings are joined, or the isoquinoline is similar but has the nitrogen 2 positions away. And so why are these of interest? Here's some structures that are examples of antimalarial drugs. This one on the top here, this is a quinoline. It's probably one that everyone's heard of, which is quinine. And here's another one that you may be familiar with, which is also a quinoline. And this one is chloroquine, and you see at the bottom left there, there's the chloride stuck to the quinoline structure there. So I'd like to thank you for listening to this lecture, and I hear people talk quite a bit about better living through chemistry, and that's how I used to say it as well. But the actual DuPont slogan from the 1950s was not better living through chemistry. It was better things for better living through chemistry. And this actually comes from a recruiting video that DuPont put together, which you can find on YouTube. I put the link there, and you can actually watch it. It's pretty entertaining to watch. Thank you very much for